Welcome to this first unit in multivariable calculus. We talk about geometry and space, and the first subject is coordinates. Has been introduced by Descartes in 1637. So let's just organize it according to dimension. So in one dimension we have a line, the number line. We call this is the x, 0 is the origin, and then we have a unit, and maybe here a number like minus 1.2. That's a point on the number line, and so there's a positive axis here and a negative axis, and that's the one-dimensional space. In two dimensions it's already more interesting, where we have two coordinates. We just take here also a unit. This is the x-axis, usually points to the right, the y-axis up, and let's just take here a point P is equal to 1, 2. This means the x-coordinate is 1, the y-coordinate is 2. So there are two coordinates, and there are also there's an origin here. This is the 0, the origin, and so this is the x-axis, the y-axis, and we have 4 quadrants. In 3 dimensions we usually draw the coordinate system like this. We have the x-axis coming forward, then the y-axis here, and the z-axis pointing upwards, and then we have 3 coordinates for every. So we have 1, maybe 1, 2, and then 1, that would be this point here. 1, 2, 1, that would be this point here. P is equal to 1, 2, 1. We have 3 coordinates, and so we have 8 octants. The first one is when all the coordinates are positive. That's the one coming forward here. And so we have also coordinate planes. So we have the xy, the yz, and the xc coordinate plane. 3 coordinate planes, and then there are also three axes. So this is 1 dimension, this is 2 dimension, this is 3 dimension, and we could go forward also to arbitrary dimensions, but that's the arena we are going to work with, just to get a little bit of so in 4D we would have 4 coordinates. A point would have 4 coordinates, like 1, 2, 3, 1. And in each of these spaces we can also draw the cube, kind of the unit cube. That would be here. In this case it's a unit square. In this case it's a unit cube. And in 4 dimensions it would be a 4-dimensional cube, which you might have heard the name, is also called hypercube or tesseract. So in the 1800s, this was has been started to be investigated by Ludwig Schläfli, Swiss mathematician, and so also the name tesseract comes from this time. So that's all about coordinates, and in the next section we look at distances. Well, here you see a picture of René Descartes teaching Queen Christina from Sweden. She liked to learn mathematics early in the morning, which Descartes didn't really like very much. To get up early, he liked to sleep long. And but you see him here happily teaching geometry. Distances, let's look at the 2-dimensional case first. Let's take a point like 1, 1. And maybe I take a point here, Q is equal to 4, 5. So if we compute the distance between these 2 points here, I mean just how long do you need to travel to go from here to here? And you might know already the Pythagorean theorem, which tells you how to compute here the distance by the sum of the squares. But it's important that we define here the distance. There are different ways to define distances, but we define the distance using this motivation of Pythagoras. Pythagoras will be proven then in the next unit. So we define the distance between P and Q just as the sum of the differences, squares of the differences. So we take 4 minus 1 square plus 5 minus 1 square. In this case, this is the square root of 9 plus 16, which is square root of 25, which is equal to 5. So this distance has 5. That's one of these famous 3, 4, 5 triangles. But we take this as a definition, the distance between 2 points in general. So A, B, and x, y, we would just define as the square root of x minus a square with y minus b squared. And the same thing also in 3D, the same. We do the same, so we define the distance between 2 points in space as the sum of the squares of the differences. So plus y minus b square plus z minus c square. So for example, let me just draw the picture which kind of illustrates this. So if we have a point like 1, 1, 0, let's take this point here, P is equal to 1, 1, 0, and then we have another point like minus 2, minus 3, 12. Let's just do that. Minus 2, minus 3, 12. So I'm going up here, 12. So this is minus 2, minus 3, 12. Now, if you want to compute the distance between this point and this point, you see that's kind of difficult to visualize a little bit. You see also here we are essentially kind of going down here. But what helps is that we kind of, we take first, we take this, you know, this distance here is 12 here, and then we take another, this distance is in the xy plane, and then we can have a right angle triangle. One doesn't really see that it's a right angle triangle, but then we get here a triangle which is also by Pythagoras. It's defined as this is z minus c square here, and this is the sum of the squares x minus a square plus y minus b square square root. So this distance here is the distance in the plane. So maybe that's a little bit hard to see here, but it's maybe better if you look at it here. So we have a kind of a point P and a point Q, and so what we do is to compute the distance between this point and this point. What we do is we take, this is the difference between the heights, this, and then we have here another distance square. So we have a triangle, we have a right angle triangle, which we can see here. Let me just kind of visualize this. This is this line and this line. These are perpendicular to each other. This is the distance we have in the two-dimensional case, and then we just add another coordinate. So you can explain it using Pythagoras. And but it's important to see that this is a definition. We could use other distances, like we could use x minus a plus y minus b absolute value, and that's the taxi distance a, b, and a, b, and x, y. Manhattan distance, because what we would do here, we get 1 point, and then we get another point, and what we would do is we would just take the sum of the the lengths, right? This length here plus this length. And so if you travel in it as a taxi driver in Manhattan, then you have to travel this distance, and you cannot go straight like on a like an airplane can go straight. You can directly go there. So the distance is something you can play with, but this is the most natural distance. It's the Euclidean distance. So spheres you can define in any space with a distance. You can just say the sphere of radius r is just all the points which have distance r to a given point. And so in one dimension this is actually quite boring. So the sphere consists just of 2 points. But in 2 dimensions it's already interesting. It's something which the Greeks were fascinated with already. So for example, if we have the point 1, 1, and we are interested in all points which have distance 2 from that point. So what we do is we draw a radius, and then we draw the circle around it. So this is the circle. And this is the radius, r, usually we denote it with r. And so the circle algebraically cannot be described as the set of points x, y, right? X, y, where x minus 1 square plus y minus 1 square is equal to the radius square, which is 4. We didn't take the square root here just to have that nice equation. And in general, it's just x minus a square plus y minus b square is equal to r square. This is a circle of radius r centered at a b. Now in 3 dimensions, the sphere is now really what we really have called a sphere. So we take a point and so with coordinates a, b, c, and we draw the sphere. So the sphere and then the radius here. In 3 dimensions, I usually call the radius rho. This is a Greek symbol rho. So we have a x minus a square plus y minus b square plus c minus c square is equal to rho square. A lot of Greek influence here, like this Greek letter rho. If you want to use r, that's fine, but later we will always call it rho. So I brought here a sphere. Isn't it beautiful? All the points which have a distance, fixed distance from a point. We will look a lot at spheres in this course. It's a very important object. And let's look at the following problem. What does this object here represent? I can tell you it's a sphere, but how do we figure this out? And here comes the completion of the square comes in. We want to complete that so that we can square this. So we can see it as a square. So we have here x plus 1 square. Can you see what one has to add here? So it's just b half. So squared, so this is 4, and so we get y minus 2 squared, and the z we leave like that, and of course we have to add the 1 and 4 also on the other side, so this is equal to 9. And so now with this completion of the square idea, we see that this is a sphere with a center at minus 1, 2, 0, and the radius is equal to 3. Now this idea of completion of the square is very important. It's the beginning of algebra, and it's Algaviri who had this idea in around 800. And so he looked at the quadratic equation. So if you have x squared plus bx plus c is equal to 0, and we want to solve this, what we can do is we can write x squared plus b, just move this out of the way a little bit, bx is equal to minus c, and then do this completion of the square idea. And then we can write it as x plus b half square is equal to minus c plus b half square. And this can be written as x is equal to minus b half plus minus the square root of b half square minus c. Or usually you kind of know it as this formula, minus b plus minus square root of b square minus 4a c, we have a is equal to 1 divided by 2. So this is the quadratic solution to quadratic equation, which Algorithm already figured out. He thought about this geometrically. So if you have x here, and so the area of that, so this is x squared, that's this area here, and then bx, if you take here b half, so what we get here is a b half x plus b half x, so this is this, and the whole thing should then be minus c, and what we have to do in order to complete this is this b half squared, just b squared over 4. We have to add that here to complete the square. Pretty cool idea, start of algebra, extremely important formula also, this quadratic formula for the quadratic equation. So in this whole course we will study a lot of geometric objects, but let me just look at a couple of examples. So we have already seen sphere, but let me just ask you, what is this? X squared plus y squared is equal to 1. But now in space, in R3, in three-dimensional space. So you could think that's a circle, you could think that's a sphere, because it has this, but if you look at it from let's look at from above, so that's kind of a good picture. So if you look from above, we have x squared plus y squared is equal to 1. We see here this circle. So this is x squared plus y squared is equal to 1. But we can choose c arbitrarily. So we can actually go here with z up. And what we actually have here is not a we have not a sphere, but an entire cylinder. So this is a cylinder. You practice this also in the homework a little bit. Another thing we are going to look at then this week still is when we have equations like that, linear equations. So if you look at an equation like this, what is this? And just one way to kind of visualize this is to look for points on the axis which satisfy this equation. In this case, we see that the point 1, 0, 0 is here, and the point 0, 1, 0, and also this point 0, 0, 1 is here. So you see, and we will actually talk about these planes here. So this is a plane here. So the whole thing, it's an infinite plane. This is a plane. Let me also just say maybe a last thing. So if you have x is smaller than 4, y is smaller than 9, and z is smaller than 16. What object is that? And if we draw that, so you see that the x-axis is between -2 and 2. So what we get is a cuboid or brick, and in this case it has a this has length 8 here, and this has length 18 here, and this has length 32 here, and here 18. Now, just to mention that this is not you know, completely, everything is completely understood, even in such simple situations. We will talk also in the lecture more about problems. But here, in this case, we have, for example, the problem of Euler brakes. So an Euler brake is such a cuboid where all these are integers here, where this length is integers, where this length is integers, where this length is integers. So these are all integers. You in the homework you look at this a little bit. But then the open question is there a perfect Euler brake? A perfect Euler brake has also the side that the space diagonal also has to be an integer, and it's an unsolved problem, a fascinating open problem where we can also use computers to search. That's it for Unit 1.